everyone. My name is Greg Boyer, and I'm Marketing Manager for Hosokawa Micron Powder Systems. Hosokawa welcomes you and thanks you for attending the next in our educational series called Jet Milling Technology 101. Let me know if you have any questions during the presentation. Submit your questions online at any time. Please see the Q&A panel on the right side of your screen. At the conclusion of the webinar, we will try to accommodate all the questions during the Q&A session. Hosokawa is a global leader in powder processing equipment and systems, with over 1,500 employees worldwide, facilities in 5 countries, and 12 technical centers with state-of-the-art research facilities. We encourage our customers to visit our facilities, where they partner with us to develop new materials and processes on over 30 different pilot and production lines for size reduction, classification, mixing, drying, and other technologies. Hosokawa Micron Powder Systems, from 1923 with the name Fluidized Machinery, is responsible for Hosokawa's business in North America, serve food, pharmaceutical, chemical, and mineral industries. We have both chemical and pharmaceutical technical centers and a contract manufacturing facility. At this time, I'd like to introduce our presenter, Bill Brown, the manager for a Chemical and Mineral Division since 2001. Bill has an engineering degree from Rutgers University and has worked at Hosokawa for over 20 years. Time here, he has held several positions, including laboratory engineer, field service engineer, and a project engineer, and has involved in hundreds of powder processing installations worldwide. Bill?
Thank you, Greg. Let me begin by outlining the topics that will be covered in this presentation. First, an overview of mill types, as well as general mill theory. Types, materials, material characteristics, and the milling. General functions and features of jet mills, then jet mill types, as well as principles, advantages, and disadvantages. By a comparison of these presented jet mills and a brief summary on their unmilling. By a question and answer forum. Milling is an extremely energy-intensive and highly inefficient process. Over the past couple of centuries, there's been extensive research in trying to determine the amount of energy to fracture a particle. For example, Ohm's law establishes that energy consumed is inversely proportional to the product size, while K's law states that for geometrically similar size reduction, the energy required per unit volume is constant. Whereas Ohm's law, it's more or less a compromise of Rittiger and Kick. However, it's important to note here that to make these 3 very significant findings, there's not one particular law that applies across all applications. Research has been done over the years, including theories from Hertz relating to stress on a particle surface, Rump's particle fracture theory in 3 steps or stages, Rickert and Vogel's direct function that the probability of particle breakage depends on initial particle size as well as mass-specific impact energy. Robertson-Rose theory that the stress energy to cause a particle fracture increases when the particle size decreases. Despite all have their flaws and cannot apply across the board. Therefore, no single method truly exists to predict the grinding behavior based solely on material properties. Here you will see a chart of various types of mills, both wet and dry, and their general product size ranges. The focus of this presentation or webinar is on jet mills, and as you can see, on the horizontal axis we have particle size, referenced by D50 or median particle size. The jet mill range, or the capability for jet milling, is to a median size of roughly 1 to 2 microns. In this next chart, we comparison of various mill types with respect to product size. In this case, D97, where D7, for example, looking at this component here, 5 microns, that means that 97% of the product is finer than 5 microns. On the axis, we have material hardness. and measured in Mohs hardness. Again, the objective of this presentation is to talk about and compare jet mills. So as you can see in this red square, now your jet mill is again capable of milling down to a median of about 1 to 2 or D97 of around 2 to 3 microns. But the fact that jet mills are able to size reduce even most abrasive of materials. Is a list of material characteristics that affect how easily a particle can fracture or reduce in particle size. Some characteristics include friability, whether the material is easy to grind or if it's non-friable or more difficult to grind, whether the material or particles are abrasive or perhaps heat sensitive, fibrous, meaning needle-like or have long aspect or high aspect ratios. In cases of fibrous materials, the way particular particles are conveyed in a medium inside of a milling chamber, depending on the orientation of those particles, it influences definitely on how they fracture, and whether the particles are sticky or wet or oily to some degree. From the previous slides, that material characteristics truly affect how well a particle can fracture. Jet mill stacks up against other types of mills, notably mechanical impact or grinding mills or medium mills. We also observed that jet mills can grind particles to an ultrafine particle size distribution and can also reduce even the most hard and abrasive materials. So what is a jet mill? A jet mill is an ultrafine grinder which uses much higher kinetic impact energy than mechanical grinding. Mills, a compressed fluid at a specified pressure flows through a converging diverging nozzle, reaching supersonic velocities. The high velocity gas carries these particles inside the milling chamber, and these particles either collide off each other, particle upon particle collision, or against surfaces inside the milling chamber. When you use a jet mill? Well, first there's a need for ultrafine particle size distribution, for which perhaps mechanical milling simply cannot achieve. There will also be a requirement for a very narrow particle size distribution, a smaller standard deviation. For example, there may be a particular product for which ultrafines below, say, 2 microns pose problems for the product, or perhaps some above 10 microns result in some clogging inside of a die of some sort. Reasons why, again, milling of hard or abrasive materials, or their high purity specification. Certain types of jet mills that can be used, or say for electronics applications, where even the smallest of iron contamination could pose for major problems. There could be heat sensitivity issues due to the fact that essentially a zero or temperature rise across a jet mill. Also potentially sanitary conditions. Despite the fact that jet mills can reduce particles down to ultrafine particle sizes, they come at a cost, however. These typically require much more energy or high energy consumption than mechanical impact and even medium mills. They require air compressors, which of course consume a great deal of energy. In addition, they typically have limited production capacity compared to other impact with medium mills, due to their dependency on these compressors, either air compressors or nitrogen compressors or other types of gas compressors. The feature of a jet mill is the utilization of a jet nozzle to accelerate the fluid, whether it be air or nitrogen or argon or even steam, as well as the particles to reach these very high impact velocities. While designs differ between the types of mills and manufacturers, one feature is that they utilize these converging diverging nozzles. One of here is a de Laval nozzle. In the case of pressurized gas upstream here accelerates in the converging zone, sonic velocities. Tension occurs in the diverging zone here, and energy driving the flow to kinetic energy, allowing for extreme high velocity impact of particles against surfaces and also against other particles. A couple notes to point out here. The gas and particles flow away from the exit of the nozzle. The velocity of the particles are lower than the velocity of the carrying gas. highest at the nozzle exit with the gradient, or delta increasing as the particles flow further and further away from the nozzle face. So, for example, here's the nozzle exit. In the case of the gas, or air, which is blue line, the blue curve here, as compared to the particle velocity, which is this pink or purplish graph here. But the nozzle exit, the velocities are very close, in the range of 450 meters per second. But as the particles and the gas flow further and further away from the face of the nozzle, for example, 50 meters away, you can see that the difference in the speeds, or the velocities, are greater. The reduction of the velocity going lower and lower of the particles as compared to the gas. Second, the subject to drag forces, affected not only by the size of the particle, but by the density and density of the particle relative to the gas, the carrying gas, that is. This slide shows the effect of gas pressure as well as temperature on the nozzle exit velocity. Here, pressures yield higher nozzle exit velocities, and here we also see the effect on the of gas and its relation to the nozzle exit velocity. So on the upper image here, we're showing a jet nozzle, and you can see the path or the velocity profile of the gas. Down below, showing graph here of the nozzle exit velocities at different pressures for two different gases. So if you were to look at the green curve here, which is for air, when comparing the nozzle exit velocities, for example, at 2 bar versus at 4 bar, you can see a notable increase in velocity from just below 400 meters per second to just below 500 meters per second. So by changing the type of gas, in this case from air to using argon, you can see effects even the same grinding pressure. Argon, the nozzle exit velocities are lower at the same pressure. You can see from this slide that gas temperatures will yield higher nozzle exit velocities. Of course, velocities relate to air impact energy. To the curve here, let's compare, say, at 2 bar, utilizing 20 degrees C grind air for a 140 degrees C grind air. At 2 bar, you can see a noticeable difference in nozzle exit velocity. So these are some important factors which affect not only nozzle exit velocities, the impact energy, and the size reduction potential. Before we begin our review of the common types of jet mills, let's consider what design factors influence or can influence the performance of a jet mill. First, nozzle type, as well as the number of nozzles utilized, and they're oriented or situated at the grinding chamber. Of course, nozzle diameter, fluid, the gas, for example, and we talked about that earlier, whether it's air, nitrogen, ethane, or argon, as well as the temperature and the pressure of that gas or fluid. How the material is fed or injected into the mill. Finally, the geometry of the grinding chamber, whether it be the diameter of the chamber, the overall size, the volume, even the shape and size of the target for jet mills. Here are common types of jet mills that we're going to review and compare today. For about target jet mills, by spiral or otherwise known as pancake jet mills, then jet mills, with fluidized bed opposed jet mills. Perhaps the oldest design of all the jet mills, with dating back over a couple of hundred, maybe 100 years or so, is target jet mill. Here I'm showing a schematic for a target jet mill. We have upstream to the right is the gas, the compressed gas. In this case, I'm showing grinding air. Gas comes in at a pressure, whether it's 2 bar or 8 bar, so it's coming to high pressure. We heat hopper or feed funnel where the material is dropping by gravity. The gas picks up, carries the particles, and together they're accelerated in this converging diverging nozzle, reaching supersonic velocities. At these speeds, the particle impact off this target, whether it be a cone shape, it could be a flat shape. So the method for size reduction is impact off target. Fractured particles, after the primary size reduction, are conveyed to the annular gap at the edge of the mill. And typically with a mill like this, downstream we would have either a cyclone for collection of powder, or perhaps with a dust collector, blower downstream to pull a vacuum and convey the powder to the collection or powder collection point. In effect, the parts have essentially one shot for primary impact off surfaces. And one common point with this type of milling mechanism is particle shape. Since particles are being accelerated at high speeds and impacting off of these plates, the parts are typically jagged in particle shape. There isn't much attrition or particle upon particle collision, so there isn't much polishing or rounding of particles that takes place inside this milling chamber. Second. Advantage of target jet mills. First, there are no moving parts, so that makes the construction and the design very simple. And since there are no moving parts, pretty low capital cost in comparison to these other types of jet mills that we'll discuss, and obviously low maintenance cost due to their simplicity. Regarding disadvantages, mentioned, the particles are accelerated and acting off these target plates at very high velocities. As you can imagine, this mill will not be good for very abrasive or even moderately abrasive materials, as you would see very high wear rates, high frequency of parts replacement. Even with slightly abrasive materials, and even if you were to wear protect the target or the inner lining of the mill, say with ceramics or perhaps the tungsten carbide spray coating, you would still see quite a bit of wear. In addition, I mentioned it's basically one shot or one primary size reduction. It's a minor secondary collisions. So due to that fact, there is no top size control. There is no classification inside the chamber. So typically with these types of jet mills, very particle size distributions are made. Another important point is feed rate. It also influences and changes the product particle size. If one were to feed at a higher capacity, for example, we expect a slightly coarser material. The points here, which are both in red and italicized, are advantages not only of target jet mills, but these are common disadvantages for all the jet mills that I will talk about. They include the fact that they require quite a bit of energy or a high energy consumption to achieve a degree of fineness. Also the fact that with all the jet mills that we're talking about, typically almost always require a pre-milling stage to actually size the material to get it into the jet milling chambers. The next jet mill is a spiral or a pancake jet mill. In this case, particles are dropped in through this transition or feed hopper, if you will, upstream, similar to the target jet mill, compressed gas source. Again, whether it's air or nitrogen or another gas. So when they say the compressed air comes in at high pressure, it up and carries the particles through this acceleration tube and into the particles into the cylindrical cross-section milling chamber. Around the perimeter of the milling chamber, we have a series of jet nozzles. These nozzles, particles, accelerate them and impel them off the inner surfaces of the milling chamber. So, do we have the mechanism of mechanical impact? The testing mechanism is really about roughly 50% mechanical impact off surfaces, but also approximately 50% particle upon particle collisions. So a mix of size reduction mechanism inside this type of mill. Typically have a blower downstream pulling a vacuum, and we have the finest outlet. Those are fine enough. As momentum, they're carried into the center and exit out and are either to a cyclone or to a dust collector. In addition, with this fines outlet tube, or in other words, an integrated static classifier, we can make adjustments with that. Typically, with some designs, make adjustments to the integrated static classifier to some degree change the resonance time and hopefully particle size for the mill. Spiral or pancake jet mills' primary parameters that do affect particle size would be, of course, grinding pressure, but that classifier tube thing that I was talking about before, as well as feed rate, similar to the target jet mill. What we see with spiral jet mills is, again, in the feed rate, we often see a different particle size distribution. And for that matter, we typically see a wide band or a span on particle size distribution. Here, process flow diagram for a spiral jet mill system. Here, looking at number 3 would be our feeding mechanism. Most commonly, it could be a volumetric screw feeder, it could be a gravimetric screw feeder, a vibratory channel, but some method to deliver the feed material at a specified uniform rate to number 4, the jet mill. Up here, I'm not showing this, but upstream would be a gas compressor, which is delivering obviously the grinding gas at its pressure. The once they're fine enough, are to a dust collector and downstream here, and of course, stream we have the system fan or system blower. One note regarding system design and the pressure loss on a system like this, we typically see pressure losses 50 inches of water column to about 25 inches of water column for a system like this. Now, look advantages for this kind of mill. First of all, even the target jet mill, which I forgot to mention before, with this type of jet mill, typically we don't see a temperature rise. We don't see heat generation during the process. Well, parts similar to the target jet mill. Moving parts, it creates some complexity, parts potential replacement, but also mechanical sources of ignition. Due to its simplicity in design, it could be designed for sanitary applications, pharmaceutical applications. More cleanability is one feature that's pretty good with this design mill. And for materials, we say that this could be considered a contamination-free grinding machine or jet mill. In the fact, if we adequately wear protect the mill with ceramics or perhaps some spray coatings like tungsten carbide, if it's a relatively soft to slightly abrasive material, typically don't see wear, and they're good enough. For numerous materials, the type of jet mill can reduce to ultrafine particle size ranges. The materials, however, due to the fact that there's no internal dynamic classifier, we can limit it on particle size on occasion. As earlier, stressing mechanism being really a mix of particle upon particle collisions, but also stressing on internal surfaces or impact. We do state of wear. So for merely abrasive materials to abrasive materials, even with wear protecting a machine like this, lining it, for example, you still tend to see quite a bit of wear with these velocities and impacting off surfaces. For occasions, since we're using this feed injector, we see a degree of blowback on occasion, so we have to make adjustments there. Also, the mill can be noisy. I mentioned before, well, for a number of materials, we tend to be able to attain ultrafine particle size distributions. There are some applications where we do need an additional downstream classifier to make that for top size or finer top size. And again, common disadvantages here are high energy consumption, as well as pre-grinding required. Here's just a few common applications for spiral jet mills. One showing here is for a 1-inch jet mill, medium particle size, capability, the tides or D97 capability. Just a snapshot or a cross-section of some different applications, whether it's pharmaceutical, chemical, mineral, cosmetic applications for an jet mill. Another jet mill. Loop mills, there's no target plate. Perhaps most similar, maybe a spiral jet mill, in that it relies on two methods of size reduction, both acting off surfaces as well as those particle-upon-particle collisions. It also have a static fines outlet similar, well, somewhat different from the spiral jet mill. In this particular case, for loop jet mills, it's a shape design. The feed material drops by gravity, is accelerated with the grinding gas, similar to the other jet mills presented. The particles are injected into the grinding zone. So in the lower portion of the chamber, we have a series of nozzles. So the grinding air comes up, goes through the nozzles, reaching supersonic velocities, and the particles impact off the surfaces in this lower grinding zone, as well as off other particles. They work in this classification area and keep them around until the particles are fine enough. They're removed, and they're here in the inner surface of the chamber, and it goes to the center and out to the tube. Perhaps major differences between a jet mill and a spiral jet mill is obviously the shape of the chamber. Whether it's, for example, the spiral jet mill is round, whereas it's donut shaped or toroidal here for a loop jet mill. The fines outlet is slightly different. Particles being pulled through opening surface and through that port. A couple of factors here, or forces. We obviously see the field and drag forces being applied here, but also something we call the Coanda effect, which contributes to the classification. At the loop jet mills, we see some advantages to the spiral jet mills. Dropping to the second one, minimum no heat generation, grinding, no moving parts. But this is also similar with the spiral jet mill, that tend to see feed rates or capacities in upwards of about 5 tons an hour. The chamber walls and the nozzles can be lined with slightly abrasive materials, and if the concentration size reduction is really in the grinding nozzle zone, not the whole perimeter or the end of the donut-shaped chamber. And we have that static tube for core materials, which could result still in ultrafine particle size distributions, yet limited with certain materials due to the fact that with certain materials, we do see perhaps the need for downstream further classification to bring particle size down. Since there's a degree of impacting off surfaces, not very positive for harder or more abrasive materials with higher wear rates. Some materials, again, downstream classification may be needed, and occasionally we do some blowback on the feed injector, as with the other types of mills presented, as well as the rate affecting the particle size distribution of the end product. The next mill we'll talk about is a fluidized bed opposed jet mill. A fluidized opposed jet mill is quite different than the other jet mills being presented. So look here on how it works. Material dropped by gravity, that matter, could be pneumatically conveyed, but for applications, it's dropped by gravity into the grinding chamber. And this here is the grinding chamber. What we stream, obviously, would be the gas compressor. So what we have is the gas manifold here, and that was through a series of nozzles that are on a single plane. Material in the grinding chamber. A combination of compressed air or flowing through the nozzles at supersonic velocities, which pick up and the particles in a grinding bed, if you will. Upstream, we have a blower pulling a vacuum on the system, so hence it's a push-pull system. We suspend the particles, the bed of material in the zone. The true mechanism for size reduction here is particle upon particle impact, with essentially no off surfaces. Chamber, we have a dynamic classifier. This is more or less a classifier wheel or like a bird cage or impeller that's rotating at a certain speed to control the top size of the product. What happens is, as the particles are reduced in size, the blower, that stream, is pulling the particles up to the center and bringing them to the classifier wheel. If the particles are fine enough, again, we're having drag and field forces acting on those particles. If the particles are fine enough, they're to the classifier wheel and are collected downstream to a cyclone or a dust collector. Once they're rejected, they're drawn outward along the chamber walls and drop down or settle at very low velocities along those chamber walls back into the grinding bed. There's internal recirculation going on until the particles are fine enough to be removed. Parameters which affect particle size include fire speed, type and nozzle size, of course, grinding gas pressure, but grinding bed level. These all affect, among things, these are the primary factors that affect particle size of the product. As before, the size reduction is through these particle upon particle collisions. Velocities along the walls, as I mentioned, along the walls, are like settling velocities. They're quite low. So we really see no wear in the grinding chamber. However, for abrasive materials, for moderately to highly abrasive materials, we do see wear in these high velocity zones, which would be around the classifier wheel. What we're doing inside of a fluidized bed opposed jet mill, we're showing a classifier wheel from the top view as well as the fines outlet. Again, this is considered the high velocity area. For applications, wear protection could be ceramic here, for example, a ceramic classifier wheel, ceramic tiles on this high velocity fines outlet area. But most abrasive materials, we may consider something like silicon carbide, shown here. Note that this type of jet mill, a fluidized bed opposed jet mill, these mills can even process abrasives, silicon carbide, boron carbide, even diamond dust, with MOSes that exceed 9.5. Here's a diagram of a common fluidized bed opposed jet mill system. This other system we show, the spiral jet mill metering device. Here's bed opposed jet mill here. The method of control to deliver the feed at a uniform rate, it could be done two different ways. Over the years, what's tested and tried, and all it would be in practice would be or decreasing the feed rate according to the power consumption or the current on the classifier motor. But the moment arrangement for a uniform feed and control mechanism would be in the mill on load cells, and the bed, hence the control point to speed up or slow down the incoming feed. Particles or product would be collected either into a cyclone to a collector. In downstream, we have a sim blower. One thing different here with this system blower as compared to a spiral jet mill blower is simply the size or pressure drop. Due to the fact that we have here with the fluid bed opposed jet mill a classifier wheel, we see a higher pressure drop. So whereas with a spiral jet mill, we may get a system loss in a range of 15 to 20 inches of water column. Of a fluid opposed jet mill, seeing system losses as low as 30 inches, but as high as 80 or even 90 inches of water column. So imagine changing the design of the blower from, say, a single-stage centrifugal fan to a multi-stage blower. The advantages of fluidized bed opposed jet mills. With the other types of mills, there's no heat generation or no temperature rise due to grinding here. This is also excellent for harder abrasive materials, as I mentioned earlier. and be equipped for contamination-free processing or purity applications. I mentioned at the beginning there are certain high purity applications, for example, in the electronics industry, where even the lowest ppm levels of iron could cause problems. So like this, the stressing mechanism is primarily or almost wholly particle upon particle collisions. Despite even with the low settling velocities in the grinding chambers along the walls, we still see a degree of iron pickup. So those can be lined with something, say for example, like a polyurethane, a cheap lining, which would prevent or any sort of iron pickup. Due to the fact that there are downstream classifiers or say an internal classifier in this mill, we have particle size control and the ability to reduce the size, particle size of the product down to really small sizes. Again, down to an earlier 1, 2, 3 micron range. The fact that it's a very stable operation, and those are typically below 82 decibels. Advantages. Before, regarding the system blower, how the system blower or the pressure drop may be as high as 80 or 90 inches of water column, as compared to a spiral jet mill at 15 to 25. So as you imagine, we envision with this high pressure drop a higher energy cost or operating cost. We could do an energy comparison with respect simply to looking at the blowers. That part of it, the electrical consumption is higher on the blower side. The capital cost is typically much higher for this type of mill versus others as well. Again, the common disadvantages here are high energy consumption and pre-processing of materials, which again common for the other jet mills in this one. Shot or a cross-section of some common applications for a fluid-bed opposed jet mill. Say from toner, range minerals, to more minerals, to abrasives themselves, ceramic materials, and pharmaceutical materials, and some other specialty chemicals and materials, for example. Various types of jet mills presented today. That all the jet mills require much more energy than other types of mills, mechanical impact mills and medium mills, and to require pre-milling or resizing. So what I'm going to do now is read each of these factors on this table or on this chart, and so each mill stacks up or compares. So what we'll do is we'll compare on the basis of particle size, span of particle size, specific energy, part shape, cost, how braided material is, and its purity. With respect to particle size and control and span, what I want to show here is what our goal on this particular slide was to try to mill a product to a D7 or top size of around 20 microns. You know that with the spiral and loop jet mill, there were similar results. To achieve that top size, since it's a wider span, we were making materials in the 3 to 4 micron range. Target jet mill quite get down to 20 microns. We were more or less like 30 microns. Similar width or span, we were milling powders down to about 4 microns. In looking at fluidized bed opposed jet mill, in order to achieve a 20 micron D97, we had a tighter particle control or span, or we made products on coarser end, so more or less a tighter particle size. The next graph shows a comparison of milling energy with these types of jet mills for most materials. So what we're here, specific energy, or the grinding energy, is measured in kilowatt hours per kilogram of output. Here, on the horizontal axis, is product D7, or nominally the top size. Here, in comparing the different types of mills, when comparing, say, greater than 20 microns on D97, the specific energies are somewhat close. However, looking below, say, 15 microns and going even finer, seeing a higher deviation or a higher difference or bigger difference between spiral and loop, the fluid head, and the target jet mill. With specific energy consumed by target jet mill to, say, achieve 6 or 7 microns, that of the spiral or the loop jet mill. With the fluidized bed opposed jet mill, energy or the advantage is finer particle sizes, say below 10 microns or 15 microns, and that specific energy is actually reduced. And I believe it's due to the function of that internal classification, top size. Final slide, I want to summarize all the factors that do have an influence. And so what we'll do is we'll go through these one by one and compare jet mills. This one, we talked about fineness. What I said earlier was, I think that potentially, or we think potentially, the fluidized bed opposed jet mill can grind it to its finest particle size due to the fact that it has an internal classification. The target mill, since it's basically one shot in, one shot out, would make the coarse. Size control internally, there is none for the target. Static out tube for both the spiral and the loop, but essentially no dynamic control. The fluid head, there is dynamic control. But I make a note with respect to top size control and specific energy. While most materials we do see lower specific energy using fluidized bed of mills, there are a number of materials where we do see similar specific energy or grinding results when a spiral jet mill to a fluidized bed jet mill. With the specific energy referring to here, with the particle shape, not that one is better than the other, but I guess depending on the application. Since early impact, we typically see a more jagged particle shape with a target. On the other end of the spectrum, due to the fact that particles are colliding off each other, and we have quite a number of secondary and third, particle collisions, we do have more of a rounded particle. With respect to capital costs, it's a no-brainer. The fluidized bed is higher in capital cost. Materials, the answer is no and no, and yes, it's regarding the fluidized bed. And for purity applications, the fact that essentially it's particle upon particle collisions, we think that the fluidized bed is the best option for that. In certain cases, the spiral or the loop jet mill would work sufficiently. Concludes my presentation. For your time and attention.
Thank you, Bill. This time we'd like to start our question and answer session. It looks like we've received quite a few questions, but we are short on time, so we're going to try to respond to a few. As a reminder, if you did submit a question during the presentation and we do not address it now, someone will contact you offline shortly. All right, we're going to take a look at the first question here. It says, I have an explosive material. Can it be processed on a jet mill?
The general answer is it probably can, most likely yes. Target jet mill or a spiral or loop or fluidized bed, depending on how explosive or the explosivity of the material is, one would consider using venting, compression, or even containment. In either of these jet mills, it would be possible to process explosive materials.
Okay. Question. What are typical pressure ranges for that mill?
Over the years, it's been more commonly in the range of, let's say, 6 to 7 bar. That's gauge. For our applications for low pressure grinding, where we're using, say, 2 bar, let's just say, generally speaking, from 2 bar to about 8 or 9 bar, most commonly in the 6 to 7 bar range for pressures.
Thank you. Next question. What wear protection is typical in a jet mill?
Well, it really depends on the jet mill and the material, but as I mentioned before, most commonly would be either a lining or perhaps a ceramic lining, trials, if you will. It could be a carbide spray coating. Those are the most common. There could be different types of hardened steels to use as well, but it does depend on how the particles are, but also the material itself. There are some certain materials where hard steel couldn't be used because there'll be a contamination So it really depends on the material.
Okay. Next question is, can you give a comparison between jet mills in terms of capacities?
It's tough to say because before that we're comparing the specific energies for a number of materials. The specific energy for a fluidized bed is lower than maybe a spiral jet mill, but you have to consider the total system, all the electrical components. So it's hard to answer that question. But then we'd have to really test the material and see what kind of output we can get. I mean, one example would be for a particular size jet mill, for one product we can do 100 milligrams an hour. The same jet mill with similar grinding airflow, it could be 2 tons an hour. So it really depends on the material.
Okay. Next question. What wear protection is most appropriate for pharmaceutical application?
Can you repeat that?
Yeah, no problem. What wear protection is most appropriate for a pharmaceutical application?
That's a good question. I handle primarily chemicals and minerals applications and not more so pharmaceutical applications. But I would think that one possible thing, wear protection, could be ceramic.
Okay. Next question. What kind of gas is usually used for abrasive materials?
Well, if the material is only abrasive and not explosive, air could be used. I mean, that's the most common, would be air. If the material is explosive, to maybe chat a little bit, if the material is explosive, one would consider using an inert gas, nitrogen, minimal oxygen content to give it that spark, if you will, to ignite.
Okay, Bill, as we are running short on time, this is going to be our last question, and just as a reminder, if Bill was unable to respond to you now, we will contact you offline. Last question. We're currently processing our material in a ball mill. What would be the advantage of using a jet mill instead?
Well, if a ball mill, one of the disadvantages of a ball mill would be the upfront capital cost. Typically, these systems get very big and very expensive. But we're already doing it. What we quickly see when we compare the medium mills to jet mills for a given product typically require about 4 to 5 times more energy than a medium mill. In some cases, even 10 times more energy. So my answer would be, if you have this installation, either keeping the medium milling and perhaps looking at downstream classification to make a product and even lower the energy consumption for that existing medium mill.
Okay, Phil. Once again, we'd like to thank everyone for joining us today. We enjoyed the presentation. As we mentioned when we first started, the program has been recorded. It will be posted to the Hosokawa website within the next 48 hours. Please feel free to review this at any time or share this with friends and colleagues. If you do have any other additional questions, feel free to contact Bill directly if regarding the technology of the presentation. Thank you very much. We hope you have a great day.